All right, let's get into it. Today, we're taking a deep dive into I2C, one of the most common communication protocols you'll find anywhere. It's an absolute workhorse, but it has some tricky spots that can cause major headaches if you're not careful. We're going to tackle three of the biggest ones: arbitration, clock stretching, and crosstalk, so your next design is totally bulletproof.
So let's start with a simple question. Think of it like an old-school party line on a telephone. What happens if two people pick up the phone and just start talking over each other? You get nothing but a garbled mess, right? It's chaos. Well, that's the exact same problem we face with I2C, because it's a shared bus. So, how does it stop everything from descending into total nonsense?
And here's the heart of it. I2C is a multi-master protocol. Now, that's incredibly powerful. It means you can have multiple brain devices, like microcontrollers, all capable of starting a conversation on the same two wires. But, and this is the important part, they can't do it at the same time. This is what sets up our very first big challenge. What happens when they try? Right. So, what actually happens when two masters try to grab control of the bus at the exact same moment? This is a situation we call bus contention, and if you don't have a system to handle it, you're looking at instant data corruption. The whole system needs a referee to step in and decide who gets the right of way. And lucky for us, I2C has that referee built right in. Its name? Bus arbitration. This is just a brilliant process that neatly solves that everybody talking at once problem. The best part is that it's non-destructive. No data gets lost in the argument. One device simply wins the right to talk, and the other one politely steps back to wait its turn.
So, how does this actually work? It's really a bit of genius, a bit-by-bit battle on the data line. As two masters start sending their data, they're also listening. Now, here's the magic. Imagine one master sends a 1, a high signal, but at the same time, another master sends a 0, a low signal. Because of how I2C is designed, that low signal is dominant. It physically pulls the line down. So the first master, the one that tried to send a 1, sees the line as low. It instantly knows it lost the argument and it drops out of the conversation. Just like that. The master that sent the low bit keeps going without a single hiccup.
So if you're designing with this, there are a few things you've got to keep in mind. First off, there's a built-in priority system. Masters with lower addresses will naturally win arbitration more often. Why? Because a lower address means they'll send a 0 bit earlier in the address sequence. Second, your device's logic has to be constantly monitoring that data line. It can't just talk, it has to listen too. And finally, the master that loses needs to be smart. It should have a retry mechanism to wait until the bus is free and then try to send its message again. Okay, so problem number 1 is solved. We know how multiple masters can play nicely together. But what about our second big challenge? What happens when you have a really fast master trying to talk to a much slower slave device that just can't keep up?
And this slide really nails the conflict. You've got the master ready to fire off the next chunk of data, like, let's go, let's go. But the slave device might be busy doing something else, like saving data to memory. It needs a way to put its hand up and say, hey, hold on a second, I'm not ready for that yet.
And the way it does that is with a really slick mechanism called clock stretching. See, the master controls the pace of the conversation with the clock line, the SCL. So the slave can just reach out, physically grab that clock line, and hold it low. This action freezes the master in its tracks, pausing the entire conversation. It is, quite literally, the I2C version of putting someone on hold. So here's the play-by-play. The master sends its request. The slave realizes, whoa, I need a second, so it pulls that clock line down to low. The master, which is always checking the clock, sees that it's low and just waits. It's designed to be patient. Then, once the slave has caught its breath and is ready, it lets go of the clock line. The line goes high again, and the conversation just picks right back up where it left off. Simple but incredibly effective. All right, so we've handled master-to-master conflicts and master-to-slave speed issues. Now we need to talk about a more physical problem, something that happens down at the wire level. What happens when the wires themselves get a little too chatty with each other? This is called crosstalk, and this is where things can get really messy.
Crosstalk is basically just signal bleed throw. The I2C data line and clock line usually run right next to each other on a circuit board. When the signal on one line changes really fast, say from high to low, it can create a little electromagnetic field that induces a tiny bit of voltage, a little glitch, on the wire next to it. And that noise can totally corrupt the clean, perfectly timed conversation we've worked so hard to maintain.
And the effects can be, well,
they can be devastating for your communication. If the data line glitches the clock line, you can get false clock pulses, throwing off your timing completely. If the clock line glitches the data line, you could flip a bit from a 0 to a 1, corrupting your data. And in the worst case scenario, really severe interference can cause one of the lines to get stuck low, completely locking up the entire bus. Nothing gets through.
Okay, that sounds pretty scary, right? A total bus lockup? But here's the good news. This is an entirely preventable problem. It all comes down to good design practices. This last part is all about how we can build a really robust system and keep those signals crystal clear. So how do we fix this? It all comes down to good physical design. Number 1, keep your I2C wires as short as you possibly can. If you absolutely have to run them over a longer distance, use shielded cables or twisted pairs to protect them. You can also just slow things down. Lowering the I2C clock speed makes the signals change less aggressively, which reduces crosstalk. And for all you PCB designers out there, use ground planes between your data and clock traces. It's a fantastic way to shield them from each other. Now, I want to pause on this number for a second, because this is one of the most critical and practical takeaways for any I2C design, choosing the right pull-up resistor. A value like 4.7 kiloohms is a fantastic starting point for most standard designs. It hits that perfect sweet spot. It's strong enough to pull the line high quickly and fight off noise, but it's not so strong that the chips have trouble pulling the line low. Get this value wrong and your bus will be unstable. Getting it right is just fundamental. And this quote really just wraps it all up perfectly. These 3 things, they're not just rare edge cases. They are fundamental concepts you have to master. Arbitration lets multiple devices share the bus gracefully. Clock stretching lets fast and slow devices talk to each other. And preventing crosstalk makes sure the physical signals are always clean and reliable. So we'll leave you with this question. Because knowing these rules of the road, arbitration, clock stretching, and crosstalk, is really what separates a design that just kind of works on your desk from a design that is truly robust and reliable when it's out there in the real world. Thanks for joining me.